In this research laboratory, cutting-edge science and technology is getting a helping hand from an old-fashioned machine, a traditional craft loom. But instead of weaving cotton for clothing, it's making a completely new type of fabric. It's a material that will give much better protection from the effects of bomb explosions and severe weather events such as typhoons and hurricanes. The project uses Auxetic materials and is led by Professor Ken Evans at the University of Exeter. Ken is a world leader in research in this area.
An auxetic material is unusual in that it's a material which, when you pull it, does something that you would not normally expect. If you imagine pulling a rubber band, two things obviously happen when you pull it. It gets longer, and at the same time it gets thinner, and this is a very easy thing to see with a piece of rubber. Auxetic materials do exactly the opposite. When you pull them, they get longer, but at the same time they get fatter. This particular project is about blast mitigation. It's about using auxetic materials in the form of a fabric to make a textile which we can then produce a curtain material from, which will act to mitigate blasts in an explosion situation. And auxetic materials, we believe, have particular characteristics will mean that they absorb energy much more effectively than the current conventional materials. The work in this particular area is incredibly new. Although auxetics have been around for 20 years in total, the idea of putting them into a fibre, in a fabric, is something that's only been there for the last 2 or 3 years.
The hands-on work of identifying which materials need to be used, the manufacturing and testing of the yarns, and analysing the results of those tests is carried out by Dr. Mike Sloan.
The really useful thing about this research is that we're taking conventional fibres. So these are fibres, materials you can buy off the shelf. So you're talking about stretchy materials, elastomeric materials like polyurethane, and then you're combining them with a higher performance fibre like a Dyneema, also ultra high stiffness carbon fibres. And it's the method in which we combine them that gives the auxetic effect. So it's conventional materials in a helical arrangement that gives the auxetic effect. And there's a number of parameters we can change. We're looking at the stiffness ratio between the two fibres and also the angle at which the second fibre is wrapped around the middle fibre. It's a case of identifying what fibres we want to purchase off the shelf, what conventional materials we need to get. We'll characterise those in a mechanical testing machine. So how strong are they, how much do they stretch? We've designed and built a purposely designed spinner here at Exeter, and we can load our core fibre onto a single spool feed spool. That's taken up at the end on a take-up spool. And we just program in the relative speeds of the actual spools, and I will manufacture a yarn, very accurately controlling what we call the wrap angle, so how tightly the wrap fibre is wrapped around the core fibre. Then that yarn will then go back to the mechanical testing machine and we'll characterise its mechanical performance, but also its shape change. How auxetic is it? When it gets this much longer, how much wider does it get? Then those most promising yarns will go forward onto our loom. The loom that we actually use is designed and sold as a craft loom. There's nothing special that we've done to the bit of equipment. There's no modifications that we've made. The only thing we do is insert our auxetic yarns to make an auxetic textile. But we actually take our auxetic yarns, load them onto what we call the shuttles. They're the noisy parts that fly left to right on the loom, and by using the computer-controlled software on the loom, we can actually change the weave pattern as well.
A crucial part of the design process involves the computer modelling work, carried out by Julian Wright, a research fellow at the university.
If we want to make enough yarn to make a curtain-sized piece of fabric, for example, that will be several hours' worth of time. So that's a very expensive mistake if we don't get the yarn right at the design stage. That's a key facet of the computer modelling, is to be able to get the yarn right without actually having to spend hours making it and then seeing if it was right. The computer modelling at this stage is concentrated on the yarns. So we're not yet modelling the textiles, and we're certainly not yet modelling the explosions. We're specifically interested in how will the yarn behave when we stretch it? How fat do we need to make it? How stiff do we need to make one or more of the components? What angle do we have to wrap the helical component at? How far can we pull it? One of the major parts of the modelling activity at the moment is to be able to predict the behaviour of the yarn from a knowledge of the two components. We know what polyurethane's like, we know what polyamide is like, for example. What we would like to know is if we wrap those two together, how will they behave? The major achievement so far of the research, certainly in the context of the computer model, is that we now have very detailed knowledge. We understand very well how to design a helical auxetic yarn. And that's a major step forward from 12 months ago, because it was all based on intuition at that stage.
The tests that the team have used to put the material through its paces show that the shock wave from a bomb blast travels more than 1,500 miles per hour. Ken and Mike explain what the tests have shown.
The very first thing you see is the light that comes from the blast, and then a pressure wave arrives from the explosion, and that moves the curtain inwards, as you might expect it to do. And then following on from that, you then get destructive damage. So if you have a glass window, the glass shatters and breaks. Now, what happens is the curtain is moved by the pressure wave first, and because our fabric is auxetic, it opens out in a particular way. The curtain at that stage is not damaged by the blast at all, and it begins to form almost like a fishing net. So the glass fragments then arrive after the pressure wave and are essentially captured by the curtain. And at this point, the curtain starts returning to its original shape. It stops ballooning out, it moves back in the other direction. And in fact, what we see is the glass fragments collected and essentially thrown back, almost like a trampoline effect, back out of the room. So you can see the energy absorbing mechanisms taking place while this process is going on. And what's been particularly useful is to be able to do the tests with very high speed cameras to see exactly what the mechanisms are, so we can understand how the total process works.
We've got pressure sensors before and after the curtains. And the two things that are really interesting are the peak pressures that we measure, but also the time duration. And when you take the area under that curve, you get what we call the impulse, and that's really the energy that's experienced as a function of the blast. And our preliminary data has shown the curtains give a 25% reduction in that impulse, so a 25% reduction in the energy that somebody the other side of the window would experience.
As well as support from the Engineering and Physical Sciences Research Council, Julian says there are a number of organisations involved in helping to take the research to the next stage.
The industrial partners in the project include the Centre for the Protection of National Infrastructure, the Home Office Scientific Development Branch, and Monofield Trading Company.
Ken hopes it won't be too long before we see the fabric in general use.
I might be being a bit optimistic here, but I would say that within 5 years you could see commercial fabrics on the market, providing they meet the promise that we believe they're going to do. We also have a spin-out company in the university called Auxetics Limited, which has grown out of the research we've been doing over the last 10 years or so, which are looking at a range of applications, and they will also be involved in the commercial development of this particular fabric. The managing director, in fact, used to be one of my research students, and he was funded on an EPSRC project as a research student. He then moved on to a postdoc for 2 years, and then after that it looked as if there was sufficient interest commercially that he then went on and set up his own company. So that company was largely started by EPSRC funded activity.
The research team say there are many potential future uses for this exciting area of work.
The intention is that the fabric should be as transparent as possible in the application areas where you want them for a curtain. Not all the fibres we are currently using are like that, but in principle there's no problem with them being transparent and having these properties.
We know that these textiles, that when you stretch them, they actually open up. So you could have a filter that could actually be self-cleaning.
Dental floss is an interesting example where if you were flossing your teeth, to have a fibre that actually expands when you pull it, filling all the gaps and cracks is an interesting idea.
Civil engineering, reinforcement of soils, storm and flood mitigation. There's a number of options for bandages. One's for wound repair. You could have an auxetic bandage that actually is impregnated with an antibiotic. You wrap that around your wound. If that was to become infected and swelled, that would place the bandage under a tension. The pores would open up and it would release the antibiotic. So it would be a smart self-healing bandage.
It's an amazingly exciting area to work in. It's particularly exciting when you explain the concept to someone who doesn't understand it. There's a moment where the light bulb switches on because it's a counterintuitive property. Auxetic materials are counterintuitive. So you have to start by explaining the conventional material, like the elastic band. When you stretch the elastic band, it gets narrower. Most things get narrow when you stretch them. And then you say, but auxetic structures get fatter when you stretch them. And there's a moment where it doesn't quite click when you're explaining, and then suddenly you see the light bulb switch on, and that's a really rewarding and stimulating moment.